In this problem, we'll be completing an ice table. We'll also be writing an equilibrium expression and then solving for the equilibrium concentration. To do that, we're going to have to use the quadratic formula. So as a review, the quadratic formula is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And of course, in order to plug values in to the quadratic equation, your expression must be written in this form. ax squared plus bx plus c equals 0. I'm sure you remember this from math class. Okay, let's start off by balancing our equation and then constructing an ice table. Okay, a 1 liter flask is filled with 1 mole of hydrogen and 2 moles of iodine at 448 degrees C. Turns out we won't even be really using that temperature. The value of the equilibrium constant is 50.5. What are the concentrations of H2, I2, and HI at equilibrium? So we're looking for the equilibrium concentrations of all three. So remember, we have a 1 liter flask and we're putting in 1 mole of hydrogen. So 1 mole in 1 liter makes 1 molar of hydrogen. We have 2 moles in 1 liter, so that's 2 molar of iodine. And initially, we won't have any product that has formed. Now, this is really all the information we have. So we know that these reactants, to some extent, will begin to form products. So what we can safely say is the concentration of these reactants will decrease and the concentration of the product will increase. Of course, we don't know how much it will increase and how much it will decrease, so we're going to just call that x. So we will say that the amount of hydrogen will decrease by some amount x. The amount of iodine will also decrease by some amount x. But notice the coefficients are 1, 1, and 2. So that means if these reactants decrease by a factor of x, that this product, well, it should increase by a factor of 2x. Now the equilibrium concentrations. We don't know what those are either, but we do know that if we start with 1 and we decrease by x, at equilibrium we should have 1 minus x. Similarly, if we start with 2 and it goes down by x, we should have at equilibrium 2 minus x. And of course at equilibrium here we'll simply have 2x. Now let's write what we know. We know the equilibrium expression. It's the concentration of the products divided by the concentration of the reactants. And remember, it's the concentration at equilibrium, so we'll be plugging in these values here. Okay? Now, in the problem, they also tell us the value of KEQ is 50.5, so we'll be able to plug 50.5 in here. So this is the same expression we had on the previous page. We just need more room to work. So let's go ahead and let's simplify 2x squared. 2x squared is 4x squared. And then in the denominator, all we've done is we've FOILed this. Remember, first, outside, inside, last. And then KEQ, that was given to us. It was 50.5. Okay, so our next step would probably be to simplify this denominator. If we have minus 1x and minus 2x, well, that can simplify, of course, to minus 3x. Now what we're trying to do, of course, is get x by itself. So let's begin to solve for x. One step we can take is we can multiply both sides by this denominator. So essentially we'll be multiplying 50.5 by each one of these factors. Okay, that's what we have on the left side, and on the right side of the equation, that will all be equal to 4x squared. Now remember that our formula, or our expression, has to be ax squared plus bx plus c equals 0. So what we're going to have to do is subtract 4x squared from both sides because we want 0 over here by itself. So ultimately, now we can use the quadratic equation once we're in this form. Okay, using the quadratic equation, this is A, that's B, and that's C. So let's plug in for A, B, and C. You should have plugged in the numbers like that. Now, of course, we just have to simplify. So we're left with something similar to this. So there's going to be two values for x. One value will be when we add these two numbers together, and the other value will be when we subtract those two numbers. So our x is either 2.34 or 0.928. Now, if you remember what x is going to be by how much the concentrations change. But in the beginning of the problem, we started off with 1 mole. If we start off with 1 mole, there's no way that we can decrease by 2 moles. That doesn't make any sense. So the only possible value for x is 0.928. So I got this from the initial problem because I said the concentration was 1. So if the concentration was 1 and x tells us how much the concentration decreases by, it's not possible to decrease by 2 if we're only starting with 1. That's why this number was the only possible value. Now, we can simply plug in x in each one of these three places. Because remember, what we're ultimately looking for are the equilibrium concentrations. And at equilibrium, we know it's 1 minus x, 2 minus x, and 2x. So let's plug this value in for x. So the concentration of hydrogen, that's here, was 1 minus x. So 1 minus 0.928. This is the equilibrium concentration for hydrogen. Let's do the same thing for iodine. 2 minus x. So let's plug in 0.928 for x. This is the equilibrium concentration for iodine. And lastly, we know that hydrogen iodide is 2x. So 2 times 0.928. That's 1.86 molar. So these three values, these are the equilibrium concentrations. Now, you may have to watch this a second time. There's a lot going on here, and these type of problems are the most difficult ones we do all year. So be sure to work through these slowly and methodically.